All right, so we're just going to continue our study of matter. Matter is made up of atoms. These atoms are going to be either in the form of elements, right? Elements, compounds, or mixtures. So that's typically what we study. Mixtures being mixtures of elements and compounds, or mixtures of compounds, or mixtures of elements. And I talked about certain important mixtures like air. Air is a very important mixture. Isotonic saline. That's another. There's lots of important mixtures out there that we're interested in. And so these are it. So what do we want to know about elements, compounds, and mixtures? What we want to know about elements, compounds, and mixtures are the properties. So for example, why are the properties of something like hydrogen so different than helium? So one of the properties we started off with is the size. Hydrogen is a different size than helium, but what impact does that make on its particular properties? When we think about properties, we're primarily concerned with what type of properties. Let's see. Yeah, chemical and physical. And so we want to understand chemical and physical properties. And I talked about the physical properties. Physical properties, you don't see any change in chemical identity. Chemical properties, these are typically chemical reactions. And so we know that these elements are going to have different chemical and physical properties as well as compounds. And then when you mix them together, those will have different properties than the component constituents sometimes. And so we'll keep track of that. And so, well, how do we study? So for example, if I asked you, what are the chemical and physical properties of chlorine, what would you say? Maybe you have a little bit of knowledge of chlorine memorized, right? Or how did you pick up? What can you tell me about chlorine, the element? It's poisonous. How did you know that?
Chlorine gas has been used as a weapon.
Yeah, chlorine gas. So you've learned something about chlorine, and you just kind of memorized it, right? You memorized it, kind of thing, I think. Or yeah. So what else?
It's used as a cleaner or something.
Yeah, disinfectant, cleaner.
Destroys the ozone layer.
Yeah, can destroy the ozone layer for sure.
It's a gas at room temperature.
It's a gas at room temperature. Good.
It's got a particular odor to it.
It's got a particular odor. It's a very corrosive odor. Yes. Yellow green gas. Yeah, you guys already have a lot of knowledge of chlorine, it sounds like. Another thing you can add to it is, chlorine atoms. When we think about chlorine, we normally think of atomic chlorine, diatomic chlorine, or what? Diatomic chlorine. Chlorine is one of the diatomic elements. So, typically when we think of chlorine, we think of the two atoms. Well, why do we even bother thinking about these diatomics? Because of this. When we try to understand chemistry, there's a big push away from memorization. A lot of people say, yeah, you don't need to memorize it. You can just look it up, Google it, and then you can find all the information that you need. But that's not the way to learn chemistry, because if that's the only chemistry you know how to Google, you know how to search, you can do great searches, then you have no skills, because anybody, you can write a computer program to basically do what you can do. And so to really develop some skills, you want some specialized knowledge and you want some specialized skills that would definitely, otherwise there's no use in taking chemistry if you can just search, look it up on Google. Well, so we need some basic knowledge memorized, but then we don't want to memorize everything because there's too much stuff to memorize. Because did you memorize the melting point of chlorine? Did you memorize the boiling point of chlorine, the density of chlorine, all these other things? No. And so it's a balance. When you learn chemistry, it's kind of a balance of memorizing some stuff and what? Well, if you don't have it memorized, well, I guess you could look it up, but is that it? No, that's not it, because what we want to do is we want to understand it at a deeper level. If we have an understanding of chlorine at a deeper level, maybe we can make some predictions. Maybe we can make some predictions about its density. Maybe we can make some predictions about other things, its melting point and boiling point. And so when we're thinking about science, sometimes it's not this sequence, the scientific method. The scientific method is what? Observation. These are called experimental facts. And so a lot of people, they have a lot of factual knowledge because they've just observed it. They read about it, they've seen it, this kind of thing. Those are an observation. But, if all you can do is just spit out facts, then you can't really make any kinds of predictions. So in order to make some kinds of predictions, it'd be much better, rather than maybe memorizing these random observations or random factual things, maybe you can recognize some patterns, and by these patterns then you can go beyond just Googling it, because maybe there's something not on Google. Maybe there's something where you have to recognize that there's some kind of pattern to this, and then we can kind of predict what it should be. And so there's patterns, but ultimately, scientists, a law, if we have a law, then we can just go ahead and calculate it using the law. But the law is just an equation, and it really doesn't explain much or describe much beyond the mathematical equation that we have. Ultimately, what we want is not the law. A lot of people put the law as the ultimate goal of the scientific method. The laws aren't the ultimate goal of the scientific method. What is the ultimate goal of the scientific method? Is theory. Theory is the ultimate goal of the scientific method, because if you understand the theory, because the theory is going to present you with a very fundamental picture of what's going on. If you understand the theory, then you don't have to memorize anything, because we should be able to use the theory to predict what color chlorine is. We should be able to use theory to predict everything you want to know about chlorine, right? That's ultimately what we want. We want the theory. So, for example, you could go ahead and measure the gravitational pull on Earth, by dropping masses. But let's say you wanted to know the gravity on a moon of Jupiter. If you want, you got to send a spaceship out there and measure it, right? No. What we'd like to do is we'd like to figure it out using theory, because that's how we predict it. We could use the theoretical understanding of gravity to predict what the gravity on a moon in Saturn is going to be. Well, the same thing here. If you're trying to design a new drug, let's say, do you want to go through? How would you go about doing this? If you're trying to design a new drug, let's say, one way you could do it is you could just go to the rainforest and start extracting a whole bunch of natural products, and seeing which of those natural products, being natural chemicals and plants and whatever else. And in fact, people do that. They go out in the rainforest, they extract these things, and then observe. Watch and observe. See if any of those have any kind of significant anti-cancer or other antibacterial activity. And so there are drug companies that they do this kind of stuff. They're looking for new natural products, maybe an undiscovered chemical that some plant synthesizes or some other thing synthesizes that they can use. But is that the way you're just going to take a whole bunch of factual observations? No, that's too much work. Hopefully it works. Sometimes it does work. Sometimes you get these things that happen. Like, did I talk about cisplatin, the University of Michigan? Well, a very similar story happened with penicillin. Penicillin, I guess they didn't clean the bacteria culture and just left it on the windowsill, and some spores came in, and then the bacteria ended up dying. Right? Did you hear about that? And so they were able to serendipitously, they were able to observe it, and then they saw it, and then they got the action and then discovered it. But not all drug discoveries are like that. And so if you're trying to, you can do observations like this. You can take lots of observations, but it's going to only get you so far unless you get lucky. You know, those people at University of Michigan got lucky in their observations. Pasteur got lucky with his observation of penicillin. You know, most of the time what we do is this: we do a multi-pronged approach in chemistry. And so drug companies will do the same thing. They'll do a multi-pronged approach. So if they know penicillin is an effective antibiotic, then they'll try to figure out what makes penicillin an effective antibiotic. You know, what's a fundamental description of its action. And so, and then there are a couple of approaches that people can take, because ultimately what we need to do is, you know, we got all these properties, but how do we understand the properties of things? How we understand the properties is we don't necessarily memorize. You have to, we don't necessarily memorize, but you still have to memorize. You have to memorize to get some kind of correlation. So penicillin has this property, has an antibiotic property, right? And so we need to know that it's an effective antibiotic, but then, you know, we need more. And that more that we need is usually this. The more that we need is, what is the composition of penicillin? You know, maybe there's something special about the composition of penicillin that makes it an effective antibiotic. But, you know, we could know the composition like diamond. Diamond is pure carbon. Graphite is pure carbon, 100% carbon, but their properties are so different. You know? And so not only do we need to know the composition, we need to know the structure. And so basically, you know, in other words, if we want to know how a substance operates, you know, element, compound, whatever, we have to know what it's made of and how it's put together. That's it. And so what it's made of and how it's put together, we look for patterns, you know, in this. Like certain structures might give this type of property. You know, we see a pattern. You know, all structures like this. For example, you know, all structures, all metals that adopt the gold structure are highly malleable. It's because of the way the structure is arranged. And so other things that adopt the gold, you know, the gold lattice, the crystal lattice, like gold, or would be silver. Silver adopts that, and then silver is highly malleable. You can spread it out into a thin sheet. However, magnesium isn't. Magnesium adopts a slightly different structure, making magnesium a lot less malleable than gold, and magnesium is a lot more brittle than gold. And so those types of patterns we look for, but ultimately, if we knew the theory, then you know, if we knew the theory, then we could predict everything just based on the theory. We wouldn't have to memorize anything. And so ultimately, this is why we want the theory. And what is the theory that describes chemistry? You know, when you boil it all down, the theory that describes chemistry is called quantum mechanics. Except quantum mechanics, the problem with the theory is it's very complicated. The math is very difficult. And so even if you're good with the theory is not enough. You could be a master of quantum mechanics, and I'll tell you, the pharmaceutical companies, they have them. The pharmaceutical companies are looking for new drugs. And so these pharmaceutical companies spend a lot of money. They buy sophisticated quantum mechanics programs. They have a whole bunch of quantum mechanics scientists there trying to figure out, okay, you know, penicillin has this kind of structure, it has this kind of composition. Let's make some other structures that are similar to penicillin, and then on the computer see, you know, should they be effective antibiotics or not? And so they try to build these things theoretically. But if the math is difficult, then their answers are going to be off, because if the math is very difficult, what they have to do is they have to make assumptions and they have to simplify things, which takes us farther and farther from reality. And so normally it's a multi-pronged approach. Pharmaceutical companies are going to have the same. They're going to have a multi-pronged approach. They're going to have theoretical chemists working, trying to figure out on the computer what would work best. But then they're going to have a whole bunch of experimental chemists taking actual observations. Did it really work? How effective does it work? And so you're going to have two types of approaches. One, ideally, we would love to have the theoretical approach because that way you don't have to do any lab work. You figure out what's going to work perfectly and then you make it. But since that doesn't work out so great, you have to have the multi-pronged approach where you're going to have experimental chemists try making different things to see, did it really make a difference? The same thing happened with catalytic converters. Catalytic converters used to have platinum inside them. Platinum's really expensive. And so, number one, catalytic converters were really expensive. And number two, people ended up getting their catalytic converters stolen all the time because it's very valuable. And so these companies were looking for less expensive catalysts. And so how do they do it? Well, they had a multi-pronged approach. They got the theoreticians trying to figure out what composition of metals would be effective, and then you had the experimental. And so the experimental chemists, what they did was they have a little plate like this where they can make 1,000 different formulations of catalyst and then try each one. Drug companies have the same thing. They'll make 1,000 derivatives of a drug and then see which one is most effective experimentally. And so in science it's the same thing. What we do is, okay, we definitely have to make some factual, like a certain little factual database in our minds. That is, in other words, we're going to have to memorize a lot of facts, and hopefully these facts we can kind of correlate to patterns. Usually the things that we memorize are the extremes of the patterns, the low extreme and the high extreme in the pattern. We memorize that, and then we can kind of guess in between. This is why I said with the atoms. With the atoms, a lot of people will say, oh, it goes from a big atom to a little atom. Well, that's not enough because, in science we need numbers too. And you can't just say, oh, that's a really little atom. No, people are going to want to know how little is that atom, right? And how little is that atom? And so normally we think in terms of the extremes. So for example, a helium atom is the smallest atom on the periodic table. And how big is it, roughly? It's like 30 picometers, 60 picometers in diameter, something like that. Well, how big is a picometer? Do you know how big a picometer is? I didn't really talk about it, but a picometer is extremely small. Yeah. Picometer is, you know how big a micrometer is, roughly? A micrometer. Well, a picometer. We got to do something. When I think of a picometer, I think it is so incredibly small it's impossible to see, right? And so your book likens it to like this. If there's a beach ball on the moon, could you see it from Earth? There's a beach ball on the moon. You wouldn't be able to see it from Earth. There's no way, right? And so that's what they're saying. If you're trying to look at an atom in a piece of matter, that's like trying to look at a beach ball on the moon. It's that small, right? That's the way I've always thought about that until, yesterday or the day before yesterday, did you hear about that news? Yeah, a single atom was observed with the naked eye. Can you believe that? I couldn't believe it. And then I had to think about it more because I still can't believe it.
Sure. I want to switch it at one point. I know it's broken. That one's broken. I'm going to take this one.
Yeah, you gotta watch out for those chairs.
Yeah, this one's not done either. Now I'm down. That one's for sure broken. You can see it's broken in the bottom.
We'll talk about picometers when we get into chapter 3. We're going to be talking about scientific notation and big numbers and small numbers and that kind of stuff. But this was really amazing with that. And so I just want to show this to you. This image was posted yesterday, or on this site it was just posted a few hours ago. 3 hours ago. But do you see this little dot in the center here? That's supposed to be a single atom of strontium. Strontium is kind of a big atom, so it's a single atom of strontium. But, you know, how can you see it? Is a strontium atom white? No. What they did was they shot light at the strontium atom so that it starts to glow. And so what you're seeing is a glowing strontium atom. Otherwise, you wouldn't be able to see it, of course. So they're getting it to start emitting light. And that light is being emitted from a single atom. So in the center of that white thing is the atom. You know, and then you see the glow from that atom. But it's still, that's just pretty shocking. The scale of this, I wanted to double check because they were saying this is like 2 millimeters. But if this is 2 millimeters, then that's kind of big, you know. So I gotta take a look. But it doesn't mean the atom's big, you know, because if it's glowing, the atom actually could be a lot
It's
smaller.
like when you look at a light bulb, like you see a big circle. But
Yeah, you see a big, exactly,
Smaller.
but it's actually a small light bulb or the source, yeah. And so
Yeah.
that's the same kind of deal
Yeah.
as this. But still, this is just amazing to see a single atom with your naked eye.
Could they zoom in more? That's what I'm wondering.
Well, I mean,
I wish.
well, although it's still hard, this is already zoomed in, so this is already magnified. So, I mean, still, it'd be hard to see, but you can see with the camera. Normally, you can't see. Normally, with visible light, they say, with a camera, you can't take a picture. Do you know you can take a picture of atoms, though? But you can't take it with visible light. You have to take pictures of atoms with X-rays. Yeah. And so there's a technique called X-ray crystal diffraction or X-ray diffraction where they shine X-rays. Unfortunately, there's no lens. If somebody had a lens that could refocus X-rays, then you can get an image of the atoms. Since there's no lens, they use a computer to put all the light beams back into an image. So anyway, getting back to this, then this is what we want to do. We want to be able to correlate. And so this semester we're going to be memorizing certain factual knowledge. We'll be looking for patterns, and we'll try to understand the theory of chemistry. But we have to use all this. We have to use factual knowledge, patterns, laws, and theory to gain a decent understanding of chemistry. You can't just rely on memorization, and you can't just rely on theory. You know? And so there's always those camps that say, no, memorization is bad. No, memorization is good, and memorization is important for this class. But it's not all memorization. All right, let's continue on here. Did I talk about physical and chemical properties already? I did? Okay. Did I talk about conservation of mass and energy?
Yes.
Yes?
Yeah,
Okay.
that was the last thing you mentioned last class, I believe.
Conservation of mass and energy?
Yeah.
Okay, did I talk about conservation of energy? Really?
But you covered it with the conservation of mass and energy.
All right. Okay, let me talk about what do I want to talk about now? Let me talk about this. There's still some more topics in Chapter 2, but we'll cover them when we take a look at the homework. Now, the student asked me, because some students have reached mastery level in Newton already, and they're asking what should they do? Should they answer more questions in Newton? Because you don't have to answer all the questions to hit mastery level. So for example, if you answer the first 4 questions correctly, then they give you mastery level or something like that. But you know, you can get more practice. You can go ahead and continue to answer more and more questions to build upon that mastery level, because that's some certain minimum they have cut out. And so it could be 17 questions, it could be 20 questions, but there are, I think, more than 30 questions on there. So that's always a good idea. But one thing I recommend, and did I mention this already? One thing I recommend is doing Newton, but also doing all the questions in the back of the book. Well, I recommend doing all the questions in the back of the book because at UCLA, I told you that story at UCLA, right? Well, UCLA has the complete solutions guide. You don't have the complete solutions guide. You guys have the partial solutions guide. And the partial solutions guide is not in a separate book. The partial solutions guide, where this went on? Turn this on again. Are the blue numbered problems here, and the answers are at the back. So what I wanted to do is I wanted just to start by going through some of these problems here, and just get started, or maybe get in the habit of doing something like this. Ooh, this is working okay now. Oh, maybe not. All right. And so let's take a look and review some of these problems and see if we can answer these. And so the blue numbered problems are good because we can just look up the answer quickly. But identify the following samples of matter as macroscopic, microscopic, and particulate. And I didn't talk about this, but you could look it up. Macroscopic means you could see it with the naked eye. Microscopic means you need a microscope. And particulate means it's an atom or atom or molecule, that, or something at the atomic or molecular level. And so I was going to say you need instruments to see it, but that strontium atom you could actually see with your naked eye. I mean, they had this excite it with light, but otherwise you could see it. Okay, let's take a look. Human skin cell. Is that going to be macroscopic, microscopic, or particulate? Okay, can you see skin cells with the naked eye? No, so we would need a microscope, so say microscopic. A sugar molecule. Sugar molecule, particulate. A blade of grass, macroscopic. A helium atom, particulate. A single-celled plant, too small to see with the unaided eye, microscopic. So, okay, that's not too bad. We'll jump to 3. Suggest a reason for studying matter at the particulate level, given that it is too small to see. So why bother studying things at the particulate level? Yeah, they'll affect the properties, That's where we see the structure. So for example, if you didn't study, well, I guess you could look at the crystals of diamond versus the crystals of graphite, but what's giving those different shapes of crystals? It's how things are arranged at the particulate level. We need to know the structure at the particulate level. That is how the atoms are put together. And so this is why we're starting. We're starting with, lattice, right? Molecules, this kind of stuff. Crystalline lattice. What's the other thing? Crystalline versus amorphous lattices. So we want to start thinking in terms of structure at the particulate level because that's going to affect how it behaves. In other words, its properties. All right, well, we're going to skip these ones without the answers and just go to 5 here. Using spheres to represent individual atoms, sketch particulate illustrations of a substance as it is heated from solid to liquid to the gas. And so, in the solid, we'd have the circles well arranged. Actually, we're going to see this. We're going to see this in the next thing here. So let's skip that for right now.
Is there like an adjustment on it? Like to the turn?
There is, for focus, there's focus, and then there's automatic exposure. But I think it's something wrong with that. I don't know.
You try the lighting.
Oh, that works.
Yeah, I could try putting off the light.
Whoa. That's not an LCD screen, that is an LSD screen.
That's true. Let me do this. Um,
God, I hate that shit. There really is anything, is there?
there's probably another chair.
No, I was saying about this.
Oh, that thing? Yeah, if you could figure it out, that would be good.
Okay, I'll make that. Okay. That seems to be doing something. It's got 3 modes. It's got colorful, white, and black.
Well, maybe try the black and white mode. See if that works. I'm just gonna do this.
Alright, white turn blue.
Yeah, that seems to be getting worse. It was working okay a little bit.
This is kind of decent.
Right there?
Yeah, it's kind of decent now.
You got it?
It's legible.
Okay. Then we'll continue with this.
Focus is kind of.
Oh yeah, that's better. That's black and white.
Yeah.
We do need some color. But, it's alright, thanks.
You just stand up.
Okay, classify the following as compounds or elements. Silver bromide. Silver bromide consists of silver and bromine. Is that a compound or element? Compound, yeah. Compounds are 2 or more elements combined. Silver bromide would be 2, silver and bromine. Calcium carbonate, limestone, compound. Sodium hydroxide, lye, yeah. Uranium, element. What's the symbol for uranium? Do you know? U, correct. Are there any other chairs? We out of chair?
Well, no, it worked. It's just like I hate the sound it makes when we get on and off.
Alright, you can use this chair.
That's fine. That's your chair, Professor.
That's it. Alright, tin? Element. Tin is an element. What's the symbol for tin?
And it got worse.
Yeah, SN. SN, it should be TI, but TI is reserved for another element. What's TI reserved for? Titanium. And titanium was the last one on there. And so sometimes there's a conflict in that, and so that was stanium. Okay. I don't know if the resolution is good enough.
Yeah, that's good.
Can you guys see that all right?
Yeah.
What number was I on?
Very top.
Very top. All right. We'll just continue with this here then. The word pour is commonly used in reference to liquids, but not to solids or gases. Can you pour a solid or a gas? Why or why not? So, you can pour like a solid, like salt. You pour salt on your. I mean, if the particles, the crystals of salt. In this case, particles could refer to little crystals rather than atoms or molecules. Anyway, this, can you pour gas though?
Like where the freezing
Doesn't it depend on the density?
Yeah, it depends on the density. If the gas is more dense, then you could pour it, you know. But anyway, this, I don't like this
I
question.
was gonna say, because of translational motion, would they be just talking about liquids?
Yeah.
In general? Yeah, so that's a very vague question.
It's not a great question. I don't like it, so I'll just ignore it.
That's maybe before the gas is denser than air. Maybe pour into like a fish tank, you put like a balloon that's floating above one gas and you go to air.
Which of the three states of matter is most easily compressed?
Gas.
Gas. Solids and liquids aren't very compressible. Number 11, classify each of the following properties as chemical or physical. Hardness of a diamond. Physical. Yeah, diamond's not going to change if you test its hardness. B, combustibility of gasoline.
Chemical.
That's chemical. C, corrosive character of an acid. That's corrosive character of an acid would be chemical. Because what can happen is there are different ways that you can dissolve something. So for example, if you dissolve sugar in water, you get sugar water. But if you dissolve metal in acid, in other words, if you dissolve sugar in water, evaporate the water, you recover the sugar. If you dissolve metal in acid, you evaporate the acid, do you recover the metal? No. The metal's been eaten away or corroded away. And so if they're talking about the corrosive character of an acid, that would be chemical because you aren't going to have metal water, you're just going to have some kind of solution, salt, it turns out. Elasticity of a rubber band, physical. Taste of chocolate.
Chemical.
Yeah. Taste, this is a tricky one too. This is a little bit ambiguous because just taste, your taste receptors don't change it chemically, you know. Although you have enzymes that will start breaking down the chocolate. And so that could be a little argued in other ways. Just like chlorine could be argued differently. All right, so we just continue on. Which among the following are physical changes?
A is
Blowing glass?
yes.
Physical, yeah. You just have a different shape of glass. B, fermenting grapes.
No.
Chemical. Forming a snowflake.
Yes.
Physical, yeah. Evaporating dry ice.
No physical.
Evaporating dry ice is actually physical because what happens is the dry ice is solid CO2. When it evaporates, it becomes CO2 gas in air. So it's physical.
So wait, so that's sublimation, right? When it turns from solid to gas.
Sublimation is solid to gas. And you could call it's evaporation off the solid surface that's occurring. E, decomposing a substance by heating it.
No.
That would be chemical. Right? If it decomposes, it's no longer like sugar. You heat up sugar. I think I mentioned before. It's hard to melt sometimes because sometimes it'll start to burn. You know? Well, anyway, what we're doing by going through all the questions is like this. Did I talk about this the other day? Why? You know. This is like oftentimes on tests, you know, they throw out questions. It's like, okay, here you are. You're like if you're taking auto maintenance class, let's say here, and you're learning. Oh, I want to change the oil in the car by myself. So you're just changing the oil, and you're practicing changing the oil. And then all of a sudden, on the test, they say, okay, let's go ahead and rebuild the transmission. Did I talk about this? Yeah, already? Yeah. And so this is what we're doing is at least, you know, we aren't going in there cold because if we've just been working on certain problems, and this could happen in Newton. If Newton only has one style of problem, it's only one level, then you aren't really being exposed to much else. And so here we can get exposed, and we want to expose ourselves to as many problems as possible. That way, we don't necessarily memorize things, and we don't necessarily see patterns initially. Sometimes it's very hard to see patterns. They took away our chart, you know. But sometimes when you look at things, sometimes when you look at things, it just looks like, in Chem 4, somebody asked me, do I have to memorize this? And I said, no, you don't have to memorize it. But then they think, okay, if I don't have to memorize it, then I don't have to know it, I don't have to think about it, I'll just put it aside and forget about it. That's not what I meant either. What I meant is, okay, you don't have to memorize this. Of course you don't have to memorize this, but you should see some patterns here. Do you see any patterns here?
See if I look good.
Well, there are patterns in there that you can use to predict certain things of reactivity. And so this is just a whole bunch of data here. But the thing we're doing here is this. The first time you look at all this, it's just a lot of stuff. But, and the sooner you look at it, the better, because what happens is your brain starts to make the patterns in your subconscious. You might not notice it, but your brain is starting to try to organize the information and make these with the neural connections. I was studying this when I was at UCLA, trying to figure out, the best way to study. And this type of stuff happens, so you don't, even though you think you're not working at it, you are working at it. Your brain is working at it, and your brain's trying to figure these things out. And it's happened to me many times, where all of a sudden there's a problem that might have stumped me. In fact, on a final exam at UCLA, they usually give one problem that's very hard, one problem that's much harder than the homework. And so one of the complaints, the students often mention is the exam is nothing like the homework. Well, it depends, how well do you know the homework? People who just go through it once, it's like that jumble of data that I just put up, When they see the homework, there's no pattern in there, there's nothing, and so everything's not going to be like the homework because the homework was all random, right? And so by going through this, giving yourself time and reviewing things, then you start building up this stuff, and so your brain can work. And so, like I said, at UCLA, sometimes, actually all the time, they make at least one problem way harder than anything in the homework, and that's true. And then the way harder is just usually it requires an extra step or two beyond the homework. And sometimes it isn't so hard. But anyway, there was one of those problems where I finished the exam, and one problem just stumped me. I couldn't figure out the answer, but it was close. I knew it was close, but time ran out. And so right after that test, I think that was my last test, so I walked over to Ralph's to get a bite to eat, and then when I was standing in the checkout line, boom, it hit me. Oh, so easy. Once you know it, it's easy, but before it was so hard. And so it was one of those things, I wasn't even thinking about it, and it just came to me. But that happens to a lot of people, and this is it. And so this is what we're doing. We're trying to build up this factual knowledge so that our brains can organize this into kind of patterns and stuff like that. But and this is the reason why I highly recommend doing this in addition. And it doesn't take that long, because if you don't know the answer, just look it up. It's a blue problem. Is the change illustrated below a physical change or a chemical change? This is a physical change. We have diatomic. This is what? Solid, liquid, or gas? Solid. This is, so this would be called sublimation. Chemical or physical change? Yeah, this for sure is a chemical change. This could be oxygen. We're breathing in O2. You don't want to breathe in this stuff, because this would be atomic oxygen. Atomic oxygen would be like corrosive. It'd be like breathing in chlorine. Your throat would start to burn, and your eyes would burn. Very unhealthy. That's because atomic oxygen is not so stable. Okay, let's go on to this one. Diamonds and graphite are two forms of carbon. Carbon is an element. Chunks of graphite are sprinkled among the diamonds on the jeweler's display tray. Is the material on the tray a pure substance or mixture? I don't like this question either. I don't like this question because, well, what is a substance? A substance is an element or a compound. So in a way, it's pure carbon. Both graphite and diamond are pure carbon. But diamonds and graphite are quite a bit different in terms of properties. And so I would say it's a mixture.
Obviously, it depends on what you're selling it as. If you're just selling it as carbon.
If this question were phrased, is it pure element or mixture, then I'd say it's a pure element because it's all carbon.
They're talking about just the carbon or like the mixture?
They're talking about a mixture of graphite and diamonds.
Okay, yeah, that'd be a mixture.
Yeah, a mixture. So, is it homogeneous or heterogeneous? Heterogeneous. The heterogeneous is non-uniform. Homogeneous is uniform throughout. And so, that's all right. Let's continue on. The substance in the glass below is from a kitchen tap. Is it a pure substance or a mixture?
Mixture.
It's a mixture, yeah. What if it came from a bottle of distilled water? Yeah, a distilled water should be a pure substance because the distillation process is a purification process in which you can purify the water. So it should be pure. But this is not, I mean, you look at the air bubbles trapped in the ice, etc. If you want to, argue one way or the other. Let me get the. I'm sorry, I'm out of order here, but just continue. Classify each of the illustrations below as an element or compound. A, element or compound? Element. Compound, we'd have to have two different atoms. I mean, two different elements chemically combined. This is the same. So this would be like hydrogen would be a diatomic element. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomics. They look like this. B. This would be a element. Okay, this structure is different. We call this structure,
Gas.
well, it's a gas. Yeah. Diatomic gas. And it would be a, what type of, for an element, it would be in what form? It would be a molecular structure. So molecular. However, this element does not form molecules. This element forms a lattice. So this would be like gold here, the gold lattice, B. Is that crystalline or amorphous? Crystalline. How about this one, C? Is that element or compound? This is a compound. This would be something like HCl or something like that. Hydrogen with chlorine. This one here, this is molecular or lattice? Molecular. However, this is salt, sodium chloride. The sodiums are these blue ones, the chlorines are the green ones here. And the sodium chloride form molecules or lattice? A lattice. You see no molecules, no discrete sodium chloride molecules like this. These molecules can pack together in a solid, but when they pack together in a solid, they're just held together by intermolecular forces. Whereas these atoms are held together by bonds. And look at it. And so this is a lattice. Lattice can go in different directions, but it's a compound. So we have two compounds there: a molecular compound, and a lattice, and two types of elements there. E. That's an element also. And E, is that a molecule of this element? What do you guess? Or is that part of the lattice, a little crystal of this element? This is part of a lattice. So E has a different structure. Or looks to have a different structure. Actually, than the top one. Okay. 43. Which of the following substances would you expect to be elements, and which would you expect to be compound? Calcium carbonate. I think we already did that one, right?
Yes.
Element or compound? Compound. Yeah. Let me take some more pictures here. What's the next one? Arsenic. Arsenic is an element. Do you know the symbol for arsenic? AS. AS is the symbol. AR is not arsenic. AR, do you know what AR is?
Argon.
Argon. Yeah. Actually, you should work on the next next row, which starts off with Na. Na is called sodium. Potassium is K.
Oh.
Na is sodium. Magnesium is aluminum. Silicon, phosphorus, sulfur, chlorine, and argon. Argon is the AR. All right. Uranium, potassium chloride, compound. Chloromethane, compound. If you know the names of the elements, then you can figure it out. If it's not an element, it's going to be a compound. 45, metal A dissolves in nitric acid. So here they take a metal and dissolve it in acid, and the acid eats away the metal. You can recover the original metal if you place metal B in the solution. Metal A becomes heavier after prolonged exposure to air. The procedure is faster if the metal is heated. From the evidence given, can you tell if metal A definitely is or could be an element or a compound? If you cannot, what other information do you need to make that classification? I don't like this question. What's that?
I would say that you can't, because don't you need more information on physical properties to determine if metal A is an element?
Well, metals, they're saying metal, and so if they're saying metal, and this is something that I know, but maybe you don't know, and that is when metals form compounds, they usually form compounds with nonmetals. If you have two metals together, that's what we call an alloy. And two metals together, alloys are different than compounds because alloys can have variable composition, whereas compounds have fixed composition. Now, they're saying metal A dissolves. When they say metal A dissolves, that means A is entirely metal. And so it could be an alloy that they're talking about, but A is an element, but you need more information to know this. So this is why I don't like this question. I don't like this question. And so when we talk, this is let me tell you another thing. The other thing that's often done at when I tell you sometimes they give you a question that's much harder. Right? The question is much harder because you might not have heard of it before. This question's easy. But if you haven't heard the information before, if you don't understand some of the principles involved, then it's very hard, right? Or could be potentially very hard. And so this is another reason for doing the shotgun approach to learning, trying to get exposure. Not only let me tell you, I went beyond. Not only did I hit this book, but I looked at what the next book in the next level class is. Went to the bookstore and looked at the problems there. If they have the solutions guide, I focus on the problems that are related to this and then look there. And so I get even more exposure to different things. Therefore, when I see a lot of different ways of doing things, then sometimes you don't think of these things during the test, but if you've seen it before, then you might think of, I can do this or do that, and it makes things a little easier. And so the more exposure you get, the better, especially when you're first starting out to learn. And so I'm going against the grain because the grain is, a lot of people say never open the solutions guide. Don't open the solutions guide until you've given it a serious effort. But I'm thinking of it a little differently. I'm thinking you're just building base knowledge, and from this base knowledge, then you can build up and do much more advanced problems, much harder problems. But the 45, we're going to cover problems like that later. It'll be not terribly difficult. Okay. Let's go on to 47. Okay, with 47, they're asking factory smokestack emissions. Is it a gas, liquid, or solid? It's mostly gas, but there could be particulates in there as well. It's little solid particles in there, and so and there could also be liquids. So this is why they say all. There could be droplets of water vapor or whatever else in there. And so smokestack emissions, you have that. Is it pure or is it a mixture? That's what PM stands for. Pure or mixture? It's a mixture. Is it homogeneous or heterogeneous? Heterogeneous. Yeah, invisible gas plus particles. EC. Oh, element or compound? Usually a mixture of compounds. There might be elements in there too, nitrogen, oxygen, stuff like that. And so, but we don't know. Most likely compounds. Concrete. Solid. Pure or mixture? Mixture. Homogeneous or heterogeneous? Homogeneous. Element or compound? Mostly made up of compounds. No concrete. Concrete, I saw an interesting documentary on concrete. It was about the Roman architecture. You hear about that?
Yeah, like some vocab.
Yeah, it was something like, how did they build such huge, architectural, not just architectural, but aqueducts and other things, infrastructure there. And they're talking about, well, the Romans had a good food supply, so they could devote more time to experimentation, scientific experimentation. They didn't know much about the theory, but they could take observations. And one of the observations they took is if you take limestone, calcium carbonate, and heat it. You have to heat this to very high temperature. And so calcium carbonate has this. It has a calcium, 1 carbon, and 3 oxygens. It's a solid. And you heat this to very high temperatures, you form calcium oxide. Calcium oxide is called lime. Calcium carbonate is called limestone. So calcium oxide is just a calcium atom and an oxygen atom. Both of these are lattice-type compounds. They don't form molecules. However, CO2 is another compound. CO2 forms molecules. And CO2 is a gas here. And so what they did was they just heat up the calcium carbonate to form lime. And it's lime, this is the key ingredient in making concrete. Without lime, you can't make the concrete. And so, anyway, let's go on to helium. There are other things in concrete as well. Helium, gas, liquid, or solid? Gas. Pure mixture? Pure. Now, normally when we think of helium, we think of pure. So if you buy helium for your balloons, is it pure helium? No, it's probably not, because pure, the pure you get, it's like water. The purer the water you get, the more it's going to cost you. Like they calculated the cost. Like a gallon of the water I was using at UCLA was very expensive. Just 1 gallon, because there's so much energy that went into it, and plus the apparatus that I used was so expensive. And so you can buy different grades of helium. Like for example, one of the grades we need over here is called UHP helium. You know what UHP stands for? UHP stands for ultra high purity, and it isn't 100%. UHP is 6 nines, which is 99.9999% pure. There's some impurities, and so normally when we say pure, it's pure. Yes, there could be some contaminants in there, but we don't know. It's like what do you think is purer? food grade chemicals or pharmaceutical grade chemicals? Pharmaceutical grade chemicals. Pharmaceutical grade chemicals are much purer. What do you think is purer? Technical grade chemicals, like we buy here in lab, or food grade chemicals? Technical grade chemicals are pure, and food grade chemicals aren't very pure. Most of them, they don't bother spending a lot of money purifying those. They figure out what's a little bit of lead, what's a little bit of chromium. It's still well below, standards. So, and a little bit of chromium is actually good for you. A little bit of lead probably isn't good for you, but they say, well, a little bit's not going to kill you, so it's probably okay. So anyway, food grade chemicals. And so when we say helium, well, we're just going to assume, yeah, it's pure, not a mixture. Homogeneous or heterogeneous? Homogeneous. Element or compound? Element. Hummingbird feeder solution, which is sugar water. Sugar water is gas, liquid, or solid? Liquid. Pure or mixture? Mixture. Mixtures have variable concentration. This is always something, somebody, what is the sugar content of your hummingbird feeder solution? And you could buy from two different sources. One source, they give you 0.1% sugar. Another source might be 30% sugar, You don't know. It's like you go buy a bottle of helium. If you go buy a bottle of helium, you don't know how much helium you're actually getting because it depends on what the pressure is inside that bottle. And anyway, and so it's a mixture, variable composition. Pure substances don't have; they have fixed. Homogeneous or heterogeneous? Homogeneous. Sugar water is pretty homogeneous. Element or compound? Yeah, mixture of compounds. Sugar is a compound, water is a compound. Table salt? Solid. Pure mixture?
Pure.
Well, it depends on the table salt. It depends if you want to say, if there's anti-caking agent in there, or iodine in there, or whatever else. And so you can go either way. It could be pure. They're showing some of the salt mines in Poland I saw. This is just pretty amazing. Like 173-mile long mine, and they're still mining salt out of it, or something like that. I forgot. It's just these huge salt mines. I think the salt's fairly pure in there, but I don't know. And a lot of people like sea salt. In sea salt, there's potassium chloride, magnesium chloride. That's not pure. That's a mixture of different salts. And so this is debatable. Homogeneous or heterogeneous? Homogeneous. Element or compound? Compound. So far, review is all right. What is the main difference between electrostatic forces and gravitational forces? I'm sorry?
I was saying electrostatic forces just slow down to static, right?
Electrostatic is a fancy name for electrical forces. Electrostatic. Yeah. Right. Electrostatic forces or electrical forces, unlike charges attract, like charges repel. That's it. Whereas gravitational forces, so electrostatic forces are the force of attraction between oppositely charged, and repulsions between like charges. Whereas gravitational forces are, and I didn't talk much about gravitational forces, but except for the scientific method. The scientific method, the pen falls, let's say, and it's a consistent pattern. They get some laws of motion or whatever. And then the hypothesis was there's an invisible force pulling the pen to the center of the Earth, right? What is that invisible force? And so the hypothesis is a force called gravity, which is an invisible force. And gravity acts between two masses. The mass of the pen, the mass of the Earth. And so gravitational forces are the forces of attraction between two masses. Now, there's going to be gravitational force attracting the two atoms together, but that force of attraction holding the atoms together is too weak. It's nothing. So chemists ignore that. Which is more similar to magnetic force? electrostatic force. Magnetic forces are like North Pole, North Pole. You know, North Pole, North Pole, do they attract or do they repel on a magnet? They repel. North, South attract, you know, but South, South repel, North, North repels. So opposites repel, opposites attract, like poles repel. Can two or all three of these forces be exerted between two objects at the same time? Yeah. Yeah, in fact, all three. All three. We didn't really talk about magnetic. Magnetic is not a major factor in chemistry, although it is kind of a big factor because what do theories do? What should theories do? Theories should describe the phenomena, describe the law in fundamental terms, but it should also be able to do what? Predict new unforeseen results. So in the 1950s, a group of physicists predicted the phenomena of magnetic resonance. And so what they did was they designed some experiments to go out and measure the phenomena of magnetic resonance. But they were unsuccessful. 10 years later, the electronics, the amplifiers, got better. And so another group of physicists went out to measure the phenomena of magnetic resonance and were successful. They were successful just because the electronics were better. So which group won the Nobel Prize? Well, let me say. Did the first group, the 1950s group, A? Did the second group, the 1960s group, or did both groups share in the Nobel Prize in physics? The second group won the Nobel Prize, and the first group were completely ignored, which was one of those things that happened. But that story keeps going around. And then that, you know, it was because of theoretical predictions. That's the reason we have MRIs today, because somebody used quantum mechanics, the theory, to predict that this phenomena exists, and now we have MRI machines.
So the electrostatic force is what like keeps the atom, the molecule, the atoms together.
Yes.
Isn't that the weak nuclear force?
I'm sorry?
Isn't that like the strong nuclear force?
The strong nuclear force does something else. Yeah. The strong nuclear force does not hold the atoms together. The strong nuclear force holds the nucleus of the atom together. Well, let's take a break here and then we'll continue. We'll take a 10-minute break.